Hello, I'm Mr. Rose, and today we're going to start our discussion about electric potential. Now, to recap, we're studying physics aside from getting a 5 on the AP because physics is the study of everyday life. We started with Newtonian mechanics. Newtonian mechanics is underlying all of Newton's laws, forces, gravitation, and then we got into some energy. We then jumped into the second semester of physics, which was electricity and magnetism. We've spent some time trying to connect the two, some relationship between electricity and magnetism and gravitation. And there are some concepts that we will continue to utilize because overlying concepts are the same. Something that physicists have been trying to do for a long time is relate electricity and magnetism to gravitation because there are so many similarities between them. Also because gravitation is one of the four fundamental forces and it doesn't really play well with the other three. We learned that different forces, like a conservative force and a non-conservative force, obey the same overlying rules of physics, specifically a conservation of energy, which is going to be something that comes to be important in this topic. We've also figured out at this point in time that Gauss's law, which is again an observational law in nature, is in fact a conservative force, and that has to do with electric fields and electric forces. If Gauss's law, which we can derive Coulomb's law from Gauss's law, if Gauss's law shows that the electric force is a conservative force, that means we can easily utilize our conservation of energy theory. That brings us to what we're discussing today. You can see some of it on the board behind me in electric potential. Give me 1 minute to just set that up. Okay, so to start this chapter, we have three real goals in mind. You can see them I've listed here. We want to define what electric potential is. We're going to be able to calculate the electric potential from an arrangement of charges and or charged objects, charged particles. Lastly, we're going to discuss how electric potential does relate to electric potential energy. Notice I said how they relate to each other. They're not the same thing. I'm going to say that a few times during this lecture. What do we know? We know electric potential is often just referred to as potential. Electric potential or potential is also, often given or thought of in terms of electric potential energy. The energy, as I said, that's an important concept. What that means is we're not actually studying any new concepts. We're learning some new physics and applying our old concepts and our old knowledge to that physics. So before we keep going, we're going to show that we can measure potential energy exactly as I've done before. So that means I'm going to take my potential energy, I'm going to define it as zero at some reference point. Well, what does that mean? That means if, for example, I show you my system there, wonderful garbage can sitting on a chair, very exciting, so now you know what I'm talking about. If I define that garbage can of having a potential energy of zero right now, even though it's on the chair, I'm going to now define its change in potential energy with respect to the field that it's in. If I take the garbage can and I lift it up, if I take the garbage can and I put it on the ground, I'm either increasing or decreasing its potential energy, which we know based on its position with respect to the Earth. I gave it a reference point of zero, and the reason I can change its potential energy is because of our U equals negative W, our conservation of energy. In order to change the energy, I need to do work, or the field in case, either do work with the field or against the field. Same exact thing is going to be happening in our E&M physics. In electricity and magnetism, if I have a charged particle and I put that at some infinite distance away, I can define the potential energy at that infinite distance as zero. Then when I bring it in, it doesn't matter if this is positive or negative. In my picture here, I have a little positive charged rod. This positive rod has a field. If I bring it in towards that field, that takes work. So if I define my potential energy at zero, way far away, then I move that to point P where it is now. It takes work, and if I know that I have work done, that means I've changed some energy configuration. That's what we're defining as capital V electric potential. Our capital V electric potential is our negative work per unit charge, or it is our energy per unit charge. Now, my electric potential is a scalar quantity, and if I just rearrange my equation, we can see that the potential energy is equal to my charge times some electric potential. Now, even though it's a scalar quantity, it can be positive or negative based on the field that I'm moving my object to. Remember, my electric field is defined as as the direction that a positive test charge would travel in that field. So we know that every charged particle has some kind of electric field associated with it. We know that this equation is telling me is if I place a charged particle anywhere in an electric field, again, every charged object has that electric field. If I place that charged particle anywhere in that field, then there has to be an associated electric potential at some point. I can find that with that simple arrangement of our equation. Again, I want to say one more time that clearly electric potential, capital V, is not potential energy. So to make some easy comparisons, things that I know about potential energy. Potential energy, first of all, we often associate potential energy like, oh, here's a mass, potential energy M. Here's a mass M. What's the potential energy of that? Potential energy is not given to an object. Potential energy is a property of this entire system of objects. What system? It doesn't matter. I only have one mass. It doesn't matter what I'm doing. It doesn't matter what you're doing. All I'm talking about is the potential energy of that mass with respect to the Earth in that gravitational field. We typically just don't draw a gravitational field because we know it's all coming down to the center of the Earth. Well, by comparison, I have some massive charge, negative Q. I put my positive test charge there, and I know the positive test charge is going to come into that, into that charge because that's the direction opposites attract. I know that there is some electric potential of that object right there, Q. So I have an electric potential, V, of energy per unit charge, because if I take this charge, I want to move further away, that's going to take an external force on my part. If I move an object closer to the charge, that again is going to be doing work by the field. The field is bringing that in, just like the gravitational fields here. That is our definition of electric potential in comparison to electric potential energy. Again, they are very, very related, but they're very different things. And not only are they different things in relation, if I took away the Earth, obviously the mass has no potential energy. There's nothing to do with it. That's like my object infinitely far away. If I take away my charge, there's no more electric field. Thus, my small test charge here would have no potential energy because it is the potential energy due to the system of objects, So lastly, we're going to discuss what if there's a change in potential. Well, if there's a change in potential, very simply, like we've done everything before, I have a change in potential, Vf minus Vi, which means my change in potential energy is my charge times my change in electric potential, or charge times Vf minus Vi. Now remember, the electric force is conservative. This is going to be very helpful to us. What does that mean? It means it's path independent. So if I go back very quickly to this picture, it doesn't actually matter if I'm going from here, zigzag, 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 zigzag down there, or just in that straight line. It's going to take the same amount of energy because, again, it's a scalar quantity and it's a conservative force. So now we're going to relate everything that we know. At this moment in time, we know conservation of energy, U is equal to negative W. We know that the change in electric potential energy is some charge times its change in electric potential. We know by definition work is just F dot D, a force dot distance, FD cosine theta. We know an electric field is a force per unit charge, Newton per Coulomb. What are we going to do with that? We're going to apply conservation theory. Our conservation theory to start, let's say something is moving with no external forces, just like we've done in the past to start our conservation of energy. Well, I know that my initial energy is equal to my final energy. Rearrange, I know my change in kinetic energy is just my negative change in potential energy. Apply that to what I know. If I apply that to what I know, I have my change in kinetic energy, which is equal to my change in potential energy. Obviously, there's a negative sign there. My change in potential energy is just plugging in negative Q times V minus V naught. Final minus initial, electric potential. Last, what if there is an external force? Well, if there is an external force, I can't do anything. False. We're going to do exactly what we just did. It doesn't even matter if the external force is conservative or not conservative. Remember, conservation of energy always works. You just need to be a better accountant. So it doesn't matter if my work done is conservative or not conservative. I'm going to apply it just like I've always done. My initial is equal to my final, but I added some work. So everything before, potential energy, kinetic energy, plus the work I add, has to be equal to my final potential and my final kinetic. Rearrange into a nice little master equation. Change in kinetic energy is my negative change in potential energy plus the work that I had to do. That's equal to negative Q times my delta V, or my change in potential, plus the work that I added, which makes sense. This is everything to get us started in electric potential and electric potential energy. One small sidebar that may or may not come up as we go on in the future is a non-SI unit. A non-SI unit for energy is an electron volt. Basically, it's a very simple simple unit. It's just a non-SI unit. It is the amount of energy that is required to move one electron through a potential difference of 1 volt. So 1 electron volt is 1.602 times 10 to the negative 19th joules. One last sidebar that I forgot about is our units for an electric field. We spoke about them before. You can see that I squeezed it right down at the bottom. We know an electric field is equal to 1 Newton per Coulomb. Once we figured out this electric potential relationship, we can do a little bit of derivation to also show that 1 Newton per Coulomb is equal to 1 volt per meter. That's all I have for you today on Introduction to Electric Potential. Feel free to like, comment, click subscribe, anything you'd like to do on YouTube, even share it with your friends. Let's spread physics to everybody. You have the potential. See you next time.